Hi, so in this video, we're going to look at second order differential equations that are non-homogeneous or non-homogeneous. And the difference between homogeneous and non-homogeneous is that they are a times d squared y by dx squared plus b dy by dx plus c equal to a function. And that makes them slightly more complicated. But a lot of the methods is very similar. So to solve, we need to firstly find the complementary function, which is solved in the same way as the auxiliary equation for homogeneous equations. So that's straightforward. We've already known how to do that. And then we need to find the particular integral, a function which is of the same general form as f of x on the right hand side of the equation, allowing us to have the general solution of y equals a complementary function plus the particular integral. And then, if required, we need to find the particular solution. Now, we need to think about what the general form of whatever this function is. If it is a polynomial on the right hand side, or if general form will be of the polynomial, the same polynomial to the same degree. So if it's a quadratic on the right hand side, our general form of the particular integral will be a quadratic. If it's a cubic, it'll be a cubic. If it's a linear, it'll be a linear. These take the same degree power. Okay. If it's an exponential, it will again also be an exponential, but with the same power. So if it was e to the 3x, we're going to have ae to the 3x. And in a trigonometric, we would use the general form of a wave function, so sine px plus b cos px. Okay. One caveat to this is that the particular integral cannot repeat a term from the complementary function, as then everything starts to cancel out and we can't solve for the unknowns. If that happens, in that case, you use x times the general form, or in very rare cases where that's also repeated, you then use x squared times f of x. But I've made sure that we do an example where that's included and also cover everything else. So the best way to do it is just to get into some examples. And so we are finding the general solution of d squared y by dx squared minus 3 dy by dx plus 2y equals x squared plus 2x plus 1. The whole point of this video is dealing with the particular integral. Finding the complementary function is just calculating the same as homogeneous. So if you're needing to look over that, just go and watch that video. And so believe me that when I say the complementary function of this part of the general solution is a e to the 2x plus b e to the x, which means for the purposes of this video, at least this question, we can just focus on the particular integral. So we've got a quadratic here, which means our general form of the particular integral, y, is going to equal, now this is where it gets confusing because we're already using a and b, so let's not get confusing. So I'm going to use different letters, c x squared plus dx plus e. We're trying to solve for these variables based on that particular integral, and the way we do that is we then get what dy by dx is, which is going to get 2cx plus d, and then therefore d squared y by dx squared will equal 2c. Now what we're going to do is substitute cx squared plus dx plus e in for y. This 2cx plus d in for the dy by dx, and the d squared y by dx squared in for the d squared y by dx squared, all leading to 2c minus 3 times 2cx plus d plus 2 times cx squared plus dx plus e equals x squared plus 2x plus 1. And what we can now do is simplify that. Leaving this on the right hand side, because then what I can do is look at where the x squareds are. There's only one, and that is the common factor, that is 2c. Now let's look at the x terms, where we've got negative 6c plus 2d, and none others, and then the remaining constants are 2c minus 3d plus 2e equals x squared plus 2x plus 1. Now I can equate the coefficients. Leading to 2c, the coefficient of the x squared, is equal to the coefficient of x squared here, which is 1, leading to c equals a half. Negative 6c plus 2d will equal 2. We now know that c equals a half, so we get negative 3 plus 2d equals 2. So 2d equals 2 plus 3, which is 1, so d also equals a half. And lastly, we can get 2c minus 3d plus 2e equals a constant, which is 1. We now know that c equals a half, so we get 1 minus d is a half, so we get 3 over 2 plus 2e equals 1, leading to 2e equal to 1 minus 1 is 0, plus 3 over 2 is 3 over 2, so we get e equal to 3/4. Yeah. Therefore, the particular integral is y equals a half x squared plus a half x plus 3/4. Therefore, the solution, which is complementary function plus particular integral, will be ae to the 2x plus be to the x plus a half x squared plus a half x plus 3/4. And there we go. That's our general solution to that equation. Okay, do one more. It's a lie, I'm doing two more. So here we have general solution of d squared y by dx squared minus 10 dy by dx plus 25y equals 4e to the 5x, and complementary function solves to be ae to the 5x plus bx e to the 5x. So all we should worry about for this question is the particular integral, which is going to be of the form y equals a e to the 5x. Now, the particular integral can't repeat a term from the complementary function. In this case, use x times f of x. So we can't use that because that's repeated. So let's try y equals x times a x e to the 5x. But look, they might be two different letters, but that term again is repeated. So again, we can't use it. Therefore, I need to use, in this particular case, x squared. Ax squared e to the 5x is going to be our particular integral form. So, same method before though, we've got y equals a x squared dot e to the 5x. So dy by dx will be the derivative of that, which is 2ax e to the 5x plus ax squared 5e to the 5x, which simplifies to be 2ax e to the 5x plus 5ax squared e to the 5x, and then d squared y by dx squared will again be the derivative of that, which is 2a e to the 5x plus 2ax times 5e to the 5x plus 5a dot 2x e to the 5x plus 5ax squared times 5e to the 5x, 2a to the 5x plus 10ax e to the 5x plus 10ax e to the 5x plus 25ax squared e to the 5x, 2ae to the 5x plus 20ax e to the 5x plus 25ax squared e to the 5x. So you can see how these quickly get away in terms of the amount of working. Well, let's focus purely on these. Substituting them in, so we've got d squared y by dx squared, which is going to be 2ae to the 5x plus 20ax e to the 5x plus 25a squared 25ax squared e to the 5x minus 10 times dy by dx. So we get 2ax e to the 5x plus 5ax squared e to the 5x plus 25ax squared e to the 5x, and that's all equal to 4e to the 5x. Complicated, but it's all going to simplify down, because if we see we've got an ae to the 5x and we've got no other ones of that, so that can just stay as 2ae to the 5x. We've got 28x e to the 5x minus 10 times 2ax e to the 5x, so they cancel out. And we have no other ones of that type, so that's that simplified straight away, which is handy. And then we've got 25ax squared e to the 5x minus 50 plus 25 of that, so they all cancel out, because 25 minus 50 is negative 25 plus 25 all cancel out. So it all cancels out, and we are left with 2ae to the 5x equal to 4e to the 5x. Equate the coefficients, and you get 2a equals 4. So a equals 4 over 2, which is 2, which then means a particular integral equals y equals 2x squared e to the 5x. And therefore, our solution, which is complementary function, plus bx e to the 5x plus a particular integral 2x squared e to the 5x. Okay, so that's what happens in that particular case where you cannot use the particular integral. Okay, so I'm going to do one last question. I'm going to do the full thing. It's a particular solution, but I'll show you how to do this. Okay, so we've got the particular solution of d squared y by dx squared plus 4y equals 6 cos x. So let's first get the auxiliary equation, or the complementary function. Okay, m squared plus 4 equals 0. So that is going to factorize. No, it's going to be a complex root. So we do m equals negative b, so negative 0 plus or minus square root of 0 squared minus 4 times 1 times 4 all over 2 times 1 goes negative 0 plus or minus negative 16, which we're going to change to 16i squared all over 2. So we get 0 plus or minus 4i over 2, which just becomes plus or minus 2i. So p is equal to 0 and q is equal to 2. Okay? So then our formula for the complementary function will be y equals e to the px times a cos qx plus b sine qx. E to the power of 0 is just 1, so we just have y equals a cos 2x plus b sine 2x for the complementary function. So now we've got the particular integral, which is of the form 6 cos x, so we need a wave function, and it's going to be a wave function which is the same angle. So the wave function needs to be of the form, we're already using a and b, so let's use c and d. C cos angle of the same type, which is x, 1x, so that's fine, plus d sine x. Check with the compounding function to see if we've got a repeated term. We do not, which is good. So therefore, dy by dx equals negative c sine x plus d cos x. So d squared y by dx squared will equal negative c cos x minus d sine x. Substituting that all into d squared y dx squared, we're going to get negative c cos x minus d sine x plus 4 times c cos x plus d sine x, all equal to 6 cos x. So let's simplify that out, and we get negative c cos x minus d sine x plus 4c cos x plus 4d sine x equals c cos x. Simplifying the cos x's, we get negative c plus 4c, and then we get the sine x's, which is negative d plus 4d, and that's all equal to 6 cos x. So we get cos x 3c plus sine x 3d equal to 6 cos x. Equate the coefficients. The coefficient of cos x is 6. The coefficient of cos x is 3c. So 3c equals 6. So c equals 3. No, it doesn't. It equals 2. Coefficient of sine x is 3d and 0. So 3d equals 0. So d equals 0. Therefore, our particular integral is y equals c cos x plus d sine x, which is 0, which is there. Therefore, our general solution, which is complementary function plus particular integral, will be a cos 2x plus b sine 2x plus 2 cos x. And that is our general solution. So we're halfway there. So I'll rewrite this on this time type. Oh, 17 minutes already. Such a lengthy video. So we've got the general solution of y equals a cos 2x plus b sine 2x plus 2 cos x. And we also know that x equals 0, y equals 3, and also that when x equals pi by 4, y equals 2 plus root 2. Okay. So let's substitute in this set of values, and we get 3 equal to a cos 2 times 0, which is 0, plus b sine 2 times 0, which is 0, plus 2 cos 0. So 3 equals a times cos of 0, which is 1, plus b times sine of 0, which is 0, plus 2 times cos of 0, which is 1. So we get a equals 3 minus 2, which is 1. Let's read the other set of values, where x equals pi by 4 and y equals 2 plus root 2. So we get 2 plus root 2 equals a cos, well, we now know that a is 1, so we can just replace that with 1. A cos 2 times pi by 4 plus b sine 2 times pi by 4 plus 2 cos pi by 4. So 2 plus root 2 equals cos pi by 2 plus b sine pi by 2 plus 2 cos pi by 4. Cos of pi by 2 is cos of 90, which is 0. Sine of pi by 2 is sine of 90, which is 1. cos of pi by 4 is 1 over root 2. So 2 plus root 2 minus 2 root 2 equals b, which is going to be, we could rearrange that to be 2 plus root 2 minus 2 over root 2. So let's just rationalize that denominator to see if it simplifies. So it becomes 2 plus root 2 minus 2 root 2 over 2, which they cancel out. And so yes, it does, because the root 2 cancel out, leaving 2. So that gives us b. So I'll go over that again. I rationalized the denominator, which gave me 2 plus root 2 minus 2 root 2 over 2. So we get 2 plus root 2 minus root 2, so they all cancel out, so it's just left with 2. So b equals 2 and a equals 1. Therefore, finally, our general particular solution of y equals a cos 2x plus b sine 2x plus 2 cos x becomes y equals a plus b plus 2 cos x. It's a lot of work, but equivalently it's a lot of marks in the final exam. Okay, so that is differential equations.